So I'm going to try to use this to kind of avoid going off on tangents. But I do want you to feel free to ask questions. And also, I put my contact info. I'll be happy to chat afterwards if you'd like. What I thought I'd do is invent a story, kind of to draw some more people into my field of how someone interested in group theory, specifically the symmetric group and its representations, might stumble upon Gromov-Witten theory. And these invented stories are bound to first hide a lot of stuff under the rug and also do some injustice to the mathematicians who actually had to do the hard work of discovering everything I'm going to talk about. So for the most part, I'll be following this beautiful paper. I'll be retelling, actually, this beautiful paper by Okonkov and Amitai from 2002. And there you can find a better view of the mathematics and also of the history. And maybe towards the end, I'll say a few words about this paper that I'm writing with Buryak, Pandaripanda, and Tesler, and that adds something to the story. Okay? All right, so let's start. Let's start with a question in group theory. Suppose we're giving an integer d and n non-identity conjugacy classes in the symmetric group on d elements, which I denote Ci. And we define a rational number, the Hurwitz number, as 1 over d factorial times the number of n tuples of permutations in SD, such that the product is 1 and each sigma I is required to live inside the conjugacy class Ci. And as an aside, let me mention that this is also equal to 1 over d factorial times the expectation of a product of random variables, 1 for each conjugacy class, which is essentially the value of a random character at that conjugacy class according to some distribution. So there's some normalization constants here that you need to put to make it work. OK, good. So the problem is to try to compute H and also describe some structure. What do I mean by structure? So note that two permutations are in the same conjugacy class if and only if they have the same cycle lengths. So it's natural to try to ask whether you can decompose H in some sense to these individual cycles. And another question you might ask is, can we somehow decompose H into other, computing some Hurwitz number to computing some other simpler Hurwitz numbers in some sense. And maybe we'll talk about that towards the end. OK. So the first thing you would notice, or you could notice, is that if you fix some some set of size n inside CP1, then H is equal to the number of topological covers of CP1 with Q removed, which are degree d, and such that the monodromy sigma I around the point Qi lies inside Ci. So what do I mean by that? So you can see an example here. I take a small loop around the point Q1, and I look at its inverse image. This is a bunch of circles. And basically, when I move around this loop, the fiber F gets permuted. And I require that this permutation lies in C1, in this case. OK. I think this is good. And OK, one last point is that we count covers up to isomorphism, which means we go over all the isomorphism classes, and we take a sum of 1 over the size of the automorphism group. This is, in general, the right way to measure the size of a groupoid. But OK. All right. OK, so next thing you could notice, or Riemann and Hurwitz noticed at the turn of the century, is that you can fill in the punctures. So you start from a cover as before, and now you get something called a branched cover, which is basically a holomorphic map from closed but possibly disconnected Riemann surface sigma to CP1, which is not constant on any of the connected components. And we call the points P of the domain where the map fails to be a cover a ramification points. And it's not hard to see that each such point is the germ of pi at such a point is isomorphic to the map that sends z to the a, where a is some integer greater than or equal to 2. And a point such as this arises when you fill in a cycle of length a. So in this example, it's the same example as before. I've drawn like what this filling in looks like. So over Q1, we have in this case two ramification points and one ordinary point. And at this point, this is already pretty nice because all of our problems live in the same universe of degree D branched covers. And another thing that's nice about this formulation is that you start getting the feeling that there's the condition of having a cycle of length A is local on the domain, right? It's some local condition at these points. So at this point, you might start fantasizing that maybe there's this nice space M, which parameterizes all the degree D branched covers. I need to add these marked points here. You'll see why in a minute. But so these are just some n tuple of marked points in the domain. No condition at this point. And maybe also the subspaces where I place, which I denoted WIQA, where I require the ith marked point to map to Q, some point at the base, and the germ to be isomorphic to this map, Z maps to Z to the A. Maybe these subspaces are nice subspaces. And then it's natural to conjecture that maybe the Hurwitz number, up to some easy combinatorial factor, is just equal to the intersection number of these subspaces. OK, great. I think I said everything I wanted to say. So this would have two nice upshots. One is that these WIs, if they're not, we really get the cycle decomposition that we wanted to obtain from the beginning, right? Each WI is a homology class, and you could study it in its own right. For example, one thing you could immediately see is that you can use the symmetries of CP1 to show that, in fact, WIQA is independent of Q. You can choose any point at the base you want just by moving it around. And so we have this nice structure that we wanted. A second upshot is that there's a general theorem that if M is a nice space and you have, OK, maybe I should say the following. First, you can use this invariance to move all the, so S1 acts on CP1. Right? There's a natural action which just rotates CP1, fixing the north and south pole, 0 and infinity. And you can also make the WIs invariant, right? These subspaces here, just by taking Q to be 0 or infinity. And there's a general theorem that says that the intersection number of such invariant spaces can be computed locally near the fixed points in M. So that would be maybe a way to compute these numbers effectively. Now, as you can see in this slide, each of these upshots actually indicates a problem with this program. So first of all, we can't move cycles around. So you can construct an easy example with n equals 2. I'll let you think about it. There's some hint in this slide. And this is a contradiction because I've argued that a ramification point shouldn't care where it maps to, right? The conditions are the same. So it doesn't matter if it maps to Q1 or Q2 or some other Q3. And this is not a property that these Hurwitz numbers satisfy. A second problem is that there's actually a unique S1 invariant or S1 fixed point in M cover going from P1 to P1 for every degree D. And that certainly can't generate all the numbers that we see. So, and the key thing that fails is that it turns out that this space, the space of Hurwitz covers is not compact. And let me see what I wanted to say. OK. So, and if you want to get a nice space, where by nice space I mean something that behaves like a closed manifold, and in particular it supports a fundamental class, then you need to compactify it. And you compactify by adding these stable maps, which Sarah also mentioned in her talk. These are holomorphic maps from a surface with some mild singularities to CP1, which is also allowed to be now constant on some of the irreducible components. OK. And I should mention, of course, there are a lot of other challenges in making this program work, and it took decades of work of many mathematicians to realize this fantasy. But I'm going to focus only on this topological issue of compactness. And you can see already from this that it at least can solve the two problems that we mentioned. First of all, the intersection number contains now more than just the branched covers. And second, there are more fixed points. Okay, so for example, I've drawn an example of what a fixed point might look like when you include stable maps. Good. Okay. So in whatever time I have left, I want to say a few words about this open Gromov-Witten Hurwitz correspondence. So let's start by considering branched covers of the disk. So these are just holomorphic maps from a Riemann surface S with boundary to the unit disk, such that the boundary of S maps to the boundary of the disk, and the map is not constant on any component. So it's pretty similar to the definition we had before. And you can count the number of such branch covers that don't have any branchings on the boundary of the disk. Okay. So you can ask, why would that be interesting? So notice that CP1 is a union of two hemispheres along the equator, right? Two disks along the equator. And you can use that to decompose any branched cover into a bunch of disk covers of the form that I mentioned above. So in this example, I've drawn an example of how you could take a branched cover of CP1 and decompose it into four disk covers. And in this way, the open or the disk covers determine the closed covers. Oh, I should mention that you can also do the reverse. So if you give me such maps that have, that agree on the boundaries in some discrete sense, and their degree on the boundary agrees, then you can glue them back together and get an honest branched cover of CP1. And so in this sense, the numbers of the disk covers determine the closed covers. But the converse is actually not true. There are counterexamples so you really get more information from these disk covers about the closed covers. Okay. Okay, good. So I should also mention that of course the disk covers suffer the same problems. These Hurwitz numbers open Hurwitz numbers suffer the same problems that we saw before with the closed Hurwitz numbers. And in order to remedy these problems, you need to compactify. And introduce the notion of an open stable map, and then you get this open Gromov-Witten theory. There is one important difference, which also Sarah mentioned in her talk, and that is that even after you compactify, in this case, you only get a manifold with boundary, or to be precise, something analogous to a manifold with boundary, in the sense that it supports a fundamental chain. It doesn't support a fundamental class. And this problem becomes even more acute when you try to work equivariantly and you try to write down a fixed point formula. I don't have time to get into how that works, but you can see my talk from my 15 minutes from last year if you want to get a glimpse of what's involved in that. It's a slightly different setup, but it gets the idea across. And but OK, so bottom line is you can actually use this localization formula to compute these open Gromov-Witten numbers, and then use that to prove an extended open Hurwitz and open Gromov-Witten correspondence. And maybe I should mention, that these formulas, so you get these fairly explicit formulas for computing the open Gromov-Witten invariance. And it's a non-trivial fact that they satisfy this map decomposition property, the same property that the Hurwitz numbers satisfy. So it's really an interesting structure that you get. OK, I think that's pretty much it. Maybe I'll just sum up by saying that I tried to show you how you can start from a problem in group theory and representation theory and sort of see how you get to holomorphic maps and maybe get even a hint of why you would need to compactify them, or what the kind of non-trivial compactification that's involved. And also maybe gave you a glimpse of why you might be interested in maps with from surfaces with boundary to the disk. Okay, I think that's pretty much it. Thank you.